right, guys. Well, welcome. Clearly, I'm out today. What we're going to be doing today is starting a conversation about this project that I'm going to have you do. It's going to count as a project grade. It's basically a study question, a study piece. We have these in music. We pick a piece and we practice it, not only to practice that particular piece, but to hone certain skills. And I think it's nice to have a study piece in mathematics as well because it adds context to the situation, makes it come to life in a way, but also allows you to practice your skills. Some things you've learned, some things that you're going to learn. Because we've already talked about circles a little bit. You know enough about circles to be able to talk about them um, for this particular problem. So what we're going to be looking at basically as we begin this next section is this guy named Eratosthenes. Okay, section 5. His name's Eratosthenes. Okay, and he calculated something 2,500 years ago that was pretty darn cool and pretty darn accurate, especially considering the time. He calculated the circumference of the Earth. I mean, contrary to what a lot of people think, the ancients knew and understood that the Earth was indeed a spherical ball floating through space. At least Eratosthenes did. Um, Various other theories also developed amongst lay people, as you would consider them. Uh, Later on, control became solidified in religious institutions, and arguments over theoretical what was the word? Arguments over the theocracy or the science of the situation ensued for millennia afterwards. But most people, even the laymen at the time of Christopher Columbus, understood that the Earth was round. The whole idea of the Earth being flat is kind of a myth. Even people at the time, maybe some people thought the Earth was flat, but some people today think the Earth is flat. And in either case, what I'm trying to say is there's a lot of knowledge that we forgot that we knew. In all probability, we as a species have forgotten more than we currently know, and I like to kind of remind myself of that. Anyway, this guy will show us just how smart people of the ancient world were, and how important and ubiquitous geometry and mathematics are, and how they can help us understand our world, even with just information that like and with the help maybe some sticks and distances and feet. So there's a video I'm going to post along with this lecture that you can watch. I recommend that you watch it, and gives you some more context to the situation. I'll do my best here. So anyway, who is this guy Eratosthenes? It's this dude. He's clearly an ancient Greek, as much of our mathematics derives from, and we've talked about them a little bit in class. Eratosthenes was a pretty cool guy. So here's some background on him. He's best known for being the first person to calculate the circumference of the Earth. He was nicknamed Beta by his contemporaries because he was about second best at everything, and Beta second letter in the alphabet. You probably heard that word before. And Eratosthenes was the founder of the scientific chronology, which is something I didn't really know all that much about. But in either case, we're going to talk about his particular discovery of the circumference of the Earth. It's actually a pretty simple calculation. There's some things that he knew. This is a situation I'll give you. I will change the numbers. Oops. I will change the numbers so that you can't look this up, but you'll have to understand the situation, and then I'll give you guys a pop quiz at some point where you'll have to perform what we do today on that pop quiz for essentially a project grade. Okay, so you have to understand the situation that we're going to be talking about today, not just copy and paste it. You have to be a thinking machine, not just a regurgitating information machine. So let me paint this picture for you here. So let me just get a picture of the Earth real quick. So I'm just going to do a circle. Okay, and on this circle, let me zoom in. We're gonna, of course, gonna have a center. I'm gonna have to eyeball it a little bit. So there was this guy, Eratosthenes. He lived in a town called Cyrene, and in Cyrene there was a well, and he knew on a specific day of that calendar year, on a specific day in that well, there was the sun shone directly at the bottom, meaning that the sun was directly overhead. Now we know that the sun is really, really far away, and it's also really, really, really big. So I'm going to do a little arc here for the sun. Probably could have done that and this. Okay. The sun is so big. Let me see if I can paint that up. Anyway, there's the sun. Okay. And the sun has rays. That's basically what allows us to see. So I'm going to go ahead and try and draw some straight lines here. Okay, draw another straight line. That last one wasn't so good. Of course, they're supposed to be parallel. Okay, imagine that there's infinite number of these things. These are the sun's rays. So since the sun is so far away, we end up with these parallel photon rays, parallel sun rays. So this guy, Eratosthenes, knew that a certain known distance away, in the town of Alexandria, or city, I should say, one of the biggest cities in the world at the time, at the same day, the sun did cast a shadow. There was a obelisk there. An obelisk is just a tower. So there's this. Maybe I should get rid of this. Oops. Nope. Don't do that. Okay. So there's this tower there. Okay, and that tower actually does cast a shadow. That shadow is a certain distance, a certain length long. Okay, so what we're going to do is I'm actually going to take this here. I'm just going to do a little like zoomed in picture here, so that we can see what's going on really. So this is. I'm going to do it in this orientation so we can kind of see, like, this is the ground. Okay, here is my obelisk. So we knew that there was a shadow being cast. We'll have to do it in black as well. Okay, and he knew the length of this shadow, and he also knew this angle here. Okay, and what was the measure of that angle? We of course knew that this was 90 degrees, right? And so he could calculate that angle using a sextant just by like looking up, and it measures like the difference in the angle. Let me just get this calculation for you real quick. So found out that that angle was 82.8 degrees. Now, this is sort of what we think how he calculated it. We know he came up with certain values. Um, some stuff was lost to antiquity as far as history is concerned, but we do know the big pieces. The small details, like what I'm about to describe to you, may be kind of hand wavy. So if that is 82.8 and this is 90 degrees, knowing your information about the interior angles of the triangle, we don't have to add 180, right? So 180 minus 90 minus 82.8 would give you this angle here. And this angle is 7.2 degrees. Okay, so now it's time for some more context. I'm going to do some other lines here. So do this line like that. That line like this. I'm actually going to continue this. Oops. Oh, there we go. And I'll do this one here. Okay. So we knew this was 7.2 degrees. If these are parallel lines, which they are, right? And we know that this angle is 7.2 degrees, meaning, oh, if I can get in there, do in different colors, so you know what I'm talking about. We'll do it in this purple. This angle here, right? That's congruent to this angle because of vertical angle congruence theorem, right? So these purple angles here are the same. And if these are parallel lines and this is a transversal, right? Then this angle here, this purple angle, will be exactly equal to this angle, right? By corresponding angle postulate. So we've got a couple things. Here we've got the triangle sum theorem that says all the angles in a triangle add up to 180 degrees, right? We all know that, and so did Eratosthenes, because he was a student of geometry. We also knew that vertical angles are congruent, right? Vertical angle congruence theorem would help us find this angle. You know, if this angle was 7.2, then this angle is 7.2 degrees. And if that's 7.2 degrees, then so is this one, right? Because of corresponding angle postulate. Okay. So what's the big deal here? So I mean, I know I didn't draw this to scale, clearly, okay? But just so we can understand the situation, um, he actually paid somebody, okay, from to walk from his town in Cyrene, okay, to all the way over to Alexandria, because that's the only way you could actually measure distances at the time. Pay someone to actually walk it, okay. And he found that it measured. Where's my information here? He found that it measured 5,000 stadia. Stadia was just a unit of measurement at the time. Okay, think of it as like the length of a stadium. And what he reasoned was that, listen, knowing that Earth is a sphere, okay, or in two-dimensional terms, a circle, knowing that this central angle, right, something we're going to be learning about very soon that we probably should have learned about already, this idea of a central angle is 7.2 degrees. Well, then, if that central angle is 7.2 degrees, and that's directly related to this length here, okay? They're in direct proportion to each other. An arc measure, which is something we're going to learn, is in direct proportion to its central angle measure. So if I could figure out what this distance is, which you did, 5,000 stadia, I would know what this length is in proportion to the whole circle, right? 7.2 would be to 360, as 5,000 stadia would be to the full circle, right? So what he did is he probably reasoned his way through this, maybe didn't use algebra, but we're going to go ahead and use algebra since we have the benefit of working with algorithm. Okay, so 7.2 degrees is to 360 as 5,000 stadia would be to some unknown, right? And that would be the circumference of the Earth. I'll put that in parentheses. So let's go ahead and do this calculation. Okay, 5,000 times 360. Okay, that's 1,800,000. Then we have 7.2x here. We're going to divide both sides by 7.2. Okay, we get 250,000 stadia. Okay, now there's a little bit of a conversion that we have to do. Okay, that conversion is, where is that? I have it written here. 0.115 miles. So if I want to take that 250,000 stadia and convert it into miles, I'll have to do some dimensional analysis. You probably heard that in your chemistry class. So let me write that down. We know that 1 stadia is equal to 0.115 miles. Again, it's kind of a little bit of debate on that, perhaps, depending on which version of stadia you used. Anyway, let's go ahead and do this conversion. So 250,000 stadia. Put that over 1. Then you have to multiply times that number, but you want to cancel out the denominator. Okay, so 1 stadia goes in the bottom, the stadias will cancel, end up with the unit I want to end up with up top. So I just have to multiply that times 0.15 times 0.115. And we get 28,750 miles. Okay, and turns out that's pretty darn close to the actual circumference. It's pretty darn close to the actual circumference of the Earth. Let's look up this actual circumference of the Earth. See how close he was. They've given it to us, and okay, there it is right there. Measured around the equator, 24,901 miles. So he was off by 1,000 miles. Really isn't all that crazy bad considering the tools he had at his disposal. And we don't know how much of that error is due to bad conversions for stadia to miles that we know of. Like, there's no real historical context for it, like exactly how long a stadia is. It's kind of based upon certain resources. So either way, pretty cool example about how simple relationships such as central angles, etc., can lead to such a, at the time, earth-shattering result. Right? Who knew? No one had been around the world at that point. So it's pretty interesting. I want you to study this. I want you to be able to do this. I want you to be able to cite the things that are here and understand it and be able to write a little bit about it. If you have questions, we'll address them in class. But today, all your lesson is basically just take those notes. Okay, work on it yourself. Build it from the ground up. Watch that YouTube video that I post, and that'll be it. All right, guys, have a great day. Be safe, and hopefully you enjoyed the Eratosthenes little demo there. I'll talk to you soon. if I can ever stop this.